Hello, Nora.
Hey, Professor. Um, by the way, there will be a lot of questions being asked once more people are in because there's just some concerns about this week's tests and then like the continuation of homework and stuff like that. Like we've all been working together as much as we can, but there's just a
Right.
lot of stress. So just be prepared. I'm just saying.
Yeah, no problem. I did just post an announcement to let you guys know. I decided I'm definitely not testing you on 25 on Wednesday. So whatever you're doing right now to prepare for the test 4 and 5 is plenty for prepping for the final. I mean, for the test on Wednesday.
Okay, gotcha.
And I've got a lot of chapters. Ideally, I want to get through 29. I'm not sure that's going to happen, but that's just 29 and actually 31 would be the best case scenario. But if I get through
Right.
29, I'll feel pretty confident that we've gotten enough material where I don't feel bad sending you off.
Gotcha.
So
That makes sense.
and all the other ones will be extra credit, just that you're allowed to do for your own betterment, if you will.
Oh, you mean like the homework is all extra credit?
Yeah, for any chapters outside of that. So
Gotcha.
anything, for instance, I think I make like usually 38 and 39 available, and they don't say extra credit yet, but they're definitely going to be extra credit. There's no way we're going to get to them.
I got you. That makes sense. Extra credit will definitely help, especially since some of the extra credit assignments, like I guess I had missed, and then like I didn't understand the lecture material behind it, so I was like
Yeah,
also trying to get like eight other things done at the same time. But
yeah, I feel you. Oh, yeah. Like I said, I did just post the announcement, so I'll try to remember to let everybody know. But it's about that. It's about test 6, and it's also about the final. For instance, all this time I've been thinking that only Monday and Tuesday
mhm.
were classes of that last week. But I looked at the calendar when my students pulled it up today, and I realized the 31st of July is a Monday, and the second, which is the
Yeah.
last day, is a Wednesday. So the final is actually going to be on the 31st now instead of the 26th, is what I thought it was going to be.
Oh, got you. Wait, the file's supposed to be on the 26th of July?
That's what I had planned on doing it because I
Oh,
was going to make it one
okay.
class
Makes
before
sense.
the last class. But since I've
Mm,
now discovered that the 31 is that class, then the 31st will be the exam day.
got you. Okay.
Gives me an extra day in case anybody, gets
Yeah.
trapped in traffic or a car wreck or something like that.
Yeah, I do. I mean more time always helps.
Yeah,
And
exactly.
yeah, we're also trying to finish a project in lab as well.
Yeah, he said you're working
Um,
on a DC motor of some sort.
yeah, yeah. And my group is a group that decided to do our own design based
Uh,
off of someone's like previous project that they had been trying to finish.
uh-huh.
So now it's snowballing and it's just become science, as you know, which is very frustrating sometimes. So,
Yes, that is. But I
but
completely get it.
yeah, I'll just wait until more people come in to ask big questions so you don't have to repeat everything.
No problem.
I'm gonna go grab a snack.
Yeah, I just got my wife to bring me some tea. Luckily, she's awesome and likes being a wife, at least a traditional wife. Did you by any chance sign up for BritBox, Shawnee? Hello, Elron. It's only you and Nora so far.
How you doing, Professor?
Not too bad. How about you?
Uh, kind of drenched in sweat, but not too bad.
Yeah, Nora was telling me I had some concerns, so we're gonna bring you down off the building, let you relax a little bit.
If that's, I'll be right back. I'm gonna grab some chopsticks real quick.
No worries. Hey, Bohan.
Hey, Professor Younger.
Ready for action today, huh?
Yeah, last class I had some family stuff I needed taken care of.
Gotcha. How's your family doing?
They're doing great. They're doing great now.
Are they here in the States or
Yes.
okay?
Professor Younger, can I ask you some question about the I just wonder like what is our schedule for the final? Like,
Oh, yes. Yeah, I just mentioned that on my announcement, so you can double check the actual in writing stuff on the announcements part of Canvas. But basically, I'd been looking, I don't know if I looked at a calendar that had started on Monday instead of Sunday, but all this time I've been thinking August 1st was Monday and August 2nd was Tuesday. And I always make my exam the next to the last day of class. So I've been telling everybody it was July 26th. Well, today one of my students pulled up their their calendar, and I was like, wait, the 31st is Monday. So now your final will be on the 31st.
you said July 31st.
Yes, that will
So
be the final.
basically we had like 2 more weeks left, right?
Exactly, 2 weeks from today.
Okay, what is the chapters gonna be on the final? Like, what is
Well,
the
I was telling Nora that my ideal scenario is I never want to get less than chapter 31. But I might have to go as low as 29 this time.
Okay, 29, and we're on 24 now, right?
Yeah, we essentially finished 24, but I got a couple examples I'm going to work to make sure y'all know how to do it. And then we'll go into 25, which is actually a chapter that usually can be covered in a day. It's pretty straightforward.
Okay, so pretty much like we had like maybe like 3 chapters this week, and 2 chapters next week. And then the final is coming.
Yeah. Yeah. I imagine on today, like I said, I'll be doing these examples, and I don't think they'll take the same whole class, but if they do, they will. That's just the nature of it. But the 19th, I will definitely finish chapter 25 during lecture, which would be after your midterm, of course, or after your exam, of course. And then
Okay,
the 24th and the 26th will be spent on 27 or excuse me, 26 and 27 at least. So I might
okay,
be thinking 28, not sure.
all right. So I just like since I missed the class, I tried to catch up, and I did a lot like actually reading homework, all that kind of stuff, and just barely get those homework done. So pretty much like last week we had a chapter 23 and 24, right? And
Yes.
I saw you said that we're going to have another test on Wednesday, which is in person. That test cover chapter 23, 24. But at the same time, there's another online test I already did, and it's chapter
Covers those
23,
chapters.
24.
Yeah, what happened was that was supposed to be the test that would be due on Wednesday, but when I moved them back to give y'all a little bit more time because I'm taking more time, that
Mhm.
put the test that was due last night, and then the one that was due Wednesday would have been due on the same day as you have a face-to-face test, and I was like, that's kind of cruel, so I pushed it back to the 23rd, I think it is, which is this coming Sunday. So that one's this coming
So
Sunday, but it's in preparing for it, you're already preparing for the test.
okay, so we don't have the Wednesday test anymore.
Yeah, you still have the Wednesday face-to-face test, but not the online one. The online one's been moved to Wednesday. I mean to Sunday, excuse me.
But I saw the online it's the same chapter with the face to face.
Yep. And in fact, I just sent out, I posted an announcement saying that chapter 25 will not be on the Wednesday test. So it's literally going to be the same thing, but it will be comprehensive, like a final midterm type thing, specifically because I am going to take the higher of the last online or the last face-to-face test and this face-to-face test and erase the other one.
You
So
said erase the other one. Which one? I'm sorry.
so the last one we did where it was sort of what I called midterm,
Uh-huh.
and it was like 17 through 20 or 17 through 21, depending on which class it was. So
Yeah.
that one, I didn't have a lot of great results. I mean, I had some people did really well, but I had a lot of people that didn't do well. So I'm going to take the higher of that score and the score on Wednesday, and that's going to be
So
the one that
okay,
counts.
so basically we had a 3 in person, and you will take the highest 2. So if I feel comfortable with my first 2, I will probably could skip this test. Is that kind of like work?
You could escape it, but I would prefer you not, just because it's prepping you for the final. But yeah, it doesn't matter if you took a 0 on it.
Okay, so if I feel comfortable with my first in person and midterm, the Wednesday one is okay.
Yes, absolutely. It's just like I
Okay,
said, there is stuff on there that I want you to be tested on and know how to do for the
sure.
final. So it's a good chance for you to try and you'll kick butt on it even if you
Yeah,
don't.
I just have really busy weekend and
Yeah,
week.
I understand.
I was kind of not ready for this test actually.
It just sneaks right up on you, doesn't it?
Yeah, I'm not ready at all. I don't know any others, but for me, it's just like struggling on those homework, 2 chapters homeworks. It's already a lot over the weekend. Like I'm pretty overloaded for a feel like already.
Yeah, Bohan's not alone. I mean, I feel like I'm in the same boat. It's been like kind of hard to keep up lately. And plus preparing for like the final at the same time has been really stressful, and reading through chapters and doing all the homework. So it's been like for there to be another test this week to study for just felt like too much. Like it
Really,
just
I was thinking you felt like really excited and happy about it. That's what I was. Dang it.
oh no, yeah, I
I,
get
I
it.
really thought that I had made a bunch of tests on one week and was everybody's gonna be happy on that.
Oh yeah.
No. So yeah, so I did give you a reprieve, guys. So yeah, the test that is Wednesday will happen during your lab, and it will be on chapters. Well, it's actually somewhat comprehensive, so it's not unreasonable for me to put some 17, 18, 19, 20 questions in there as well, which based on the grades and everything that everybody's been doing, that shouldn't be a problem. But it's only going to stop at chapter 24. It's not going to 25. And as I just finished saying, it's going to only that one or the last one will count. So take a de-stress moment. Don't worry too much if you can't get what you consider sufficient time to study for this next test. If your last test wasn't that bad, then you'll be fine. If your last test was bad, then you probably need to make sure you do might want to start taking that practice test for test 5 right now and get 100 of those under your belt. Not 100 literally, but
Okay.
When you say the last test, do you mean the very first one we took or the proctored midterm we took?
that proctored midterm, that either that grade or the grade we get Wednesday will count, and it's the highest one of the two that counts.
Okay. And so what was that very first test we took then? That was just
You talking about at the very beginning of the semester? That's an online test, so they count less. Whereas the midterm or the face-to-face test, along with the final, all count equally, and they count as 45% of your total course grade.
I was talking about the first face-to-face one that we took.
Oh yeah, that's the one that I'm gonna erase if you didn't do that well, but you do better on this one, or it's the one you'll keep if you did better on that one than you do on this one.
Okay. And will the grades for that one be fixed? Because I only missed one, but it says I got a 9 out of 100.
Yeah, that's something I got to do. I did what I learned from Canvas administrative stuff, and it turns out that none of it fixed it. So I just got to go in there manually. I suspect I should have something. I definitely will have it by the weekend, but I might have it hopefully by Wednesday, where your whole grade book is actually functioning properly and all that good stuff.
Okay, thank you.
I'm getting ready to post a message to everyone.
Professor Younger.
Yes.
Just a quick question about the final. So you just said so we had what's the percentage of the final is gonna worse on our total grade? It's like 15 or 25? Because since we had 3 in person, so it's gonna be 15,
Uh,
15% for the final or
Oh yeah,
25?
yeah. So it basically is 45%, and I'm already dropping one of them because I never dropped the final. So really, it's 2 tests counting the 25%, and essentially they're going to be 12.5% each.
Wait, I'm kind of a little bit lost here. So
Excuse me,
you said
22.5. My fault. Maybe it's
so
better.
final was 22 and a half.
Yeah, because there's only 2 tests, and I think I divided it up over 45% total. So half of 45 is 22.5.
Oh, I saw you said we got a 3 in-person test. So we had the first
We
one.
did, but I dropped one. I'm already planning on dropping one because I told you if you do better on this one, I'll give you this grade instead of the last one. If you did better on the last one, I'll give you the last grade instead of this one. So that's
So
what
you okay, you only keep the highest 2, that including final.
Yeah, exactly.
So if I did, let's say if I did, I say that if I did good on my first one and I did good on the midterm, so even I kind of mess up with my final, I can drop the final.
You can't drop the final. The finals never drop, but like I said, the other ones will be, and that of course makes the final worth more than it would have been. But normally my finals were 25% all by itself, so I've sort of made it easier.
So before the final was 25, now the final was 22.5. Is that what you're saying?
Yes,
Okay.
22.5%.
Okay, thank you.
No problem. All right, so it appears we're not able to go beyond chapter 28. I was just going roughly through the days left in the semester, and it looks like I might not even be able to get to 29, which is what I ideally had thought. And literally, that's my second tier ideal, not my first tier ideal. The first tier ideal is at least chapter 30. What I'd rather do is up through 31. But I might just give you bits and pieces of it so we can make sense of it. Other than that, we're just going to be doing 17 through 24 are the homework assignments that you've already gotten prepared for and are not extra credit. Then we'll start if we get chapter 25, which I think we might get done. If we don't get it done tonight, we'll get it done next time. But then 26 and 27 and 28, who knows what's going to happen with those, but you'll know next week. So any chapters outside of that, 31, or excuse me, 37, 38, 39 or 40, any of those other chapters, they're extra credit, even if I didn't write extra credit on it. That's why I wrote all that in the chat, is so you'd have a written record of what might count as a homework, even though it's not listed as extra credit, or even though it is listed as extra credit.
Okay, Professor, final like summary of what was said. So the final's 22.5%. We're only going up to possibly chapter 28. And then our next test, which is Wednesday, it's comprehensive from 17 to 24.
Mm-hmm.
And it can replace our midterm grade if it's better. But
worse, you'll keep the midterm.
Right. But the first test that we ever took in person, that still counts, right? We're not getting
Yeah, I
rid of
thought the first one we ever took in person wasn't that in the midterm, or did we take another
that
one?
wasn't. No, the first test that we ever took in person was the first test we were assigned. And that one got screwed up because it was basically like a quiz, but it was like in test format. So we went in class, it was only 6 questions or something.
Gotcha. Okay, that makes it change, because if I had that one, I completely forgot. But
yeah, that one's
that
still
makes
in
it better.
Okay, so
it makes it better for you.
if okay.
Because now it's 3 instead of 2 divided over 45. That means the final and the other thing would only be 15. So yeah, I'd completely forgotten that we had done that. But
yeah, that's what I was trying to asking earlier. If finals only worth 15% now.
Yeah, it should be worth 15. Thanks for catching me on that.
Yeah, 15. Yeah, because that didn't make sense since we had 2 in person now.
Right.
And this is going to be our 3rd in-person test, and then we'll do another one for final. So that's 4. That's 4 split up, 45.
Yeah, 4, but I am dropping 1, so it'll be 3 out of them. Because, like I said, I'm taking between this test Wednesday and the last test, not the first test, but the last test. You're only getting the higher of those 2.
Gotcha.
Okay. I don't, mainly because I knew there were some issues that happened with with the midterm, from things like some students didn't have the charge of an electron, they hadn't committed it to memory and they hadn't put it on their sheet. Other cases where students took it at the testing center and I didn't get them to turn in their work like they were supposed to. I had one student, for instance, turn in the work like the next day, but I have no idea if that was really work done by them at the testing center, or if that's just something they made up after class. Because that would obviously be a lot better grade. So in light of that, I'm trying to make sure. And there was a lot of bad grades on that midterm where I don't remember them being that many bad grades on the first one.
Gotcha.
Okay.
Yeah.
All right. So everybody also, since it looks like, well, just about everybody's here. I got 7 people. The final is now going to be on the 31st. And I suspect what we can do with that is I can either proctor you myself via Zoom, meaning I'm just going to sit there and watch you guys take your test at the regular time. I don't want to make Kevin, Mr. Mitchell, do that during his lab, so I'm not going to make it the final then. The final will be during class time. So either I'll make it completely online with with Respondus Lockdown Browser and Respondus Monitor, or I'll just make sure you all have a camera and I can monitor you myself online. So be thinking about what's better for you, what's more convenient for you. And if you let me know, I'll probably do a democratic process, even though that's not the norm within education. Okay.
If we do it online, not online, but in class, will we have to have our microphones on? Because
No, you shouldn't have to.
okay.
Yeah, and a lot of people like to listen to music while they're taking their tests and stuff like that. So that's cool. I don't mind that, and I'd prefer it not to be on. But as long as you can at least hear me in case I want to know what you're doing, that'd be fine.
Just my opinion. I feel like online is more comfortable because it's more flexible. So you can manage your time and pick which time works perfectly for you. My personally like this. Like right now, it's kind of like after dinner time. It's obviously my head's like I don't know, feel like getting tired.
You're falling
And
asleep.
yeah, falling asleep a little bit is probably not the best time for me to take. It's just my opinion.
Yeah, you should look up Dr. Sean Baker and start eating like him, nothing but steak.
Okay.
Then you won't have that carbohydrate and sugar drop.
Yeah, too much soda now.
All right. So everybody, are y'all familiar with the new schedule? Please check the announcement that I posted in Canvas. I think that announcement is supposed to be emailed to you as soon as I make it, but I'm not sure. If anybody's got that email, let me know. At least then I'll know that there's an email version of the announcement that goes out. But check in the announcements and you'll see what I just announced. The test on Wednesday does not contain chapter 25. But in principle, it could be 17, 18, 19, 20, 21, 22, 23, and 24. Okay, so there's still some fair game questions, but obviously it's been so long since, we did 17, 18, 19, and 20. If I ask you those questions, they're supposed to be pretty straightforward. Okay, they're not supposed to be that hard. Stuff like, I don't know, calculating the efficiency of a heat engine, comparing it to the efficiency of the Carnot engine, ideal gas laws. Can you use PV equals nRT, or can you use P1 V1 over T1 equals P2 V2 over T2, that kind of stuff. That's probably that, and simple linear expansion due to temperature raises. Some of those little simple problems from 17 through 20 are probably really where if I decide to put them in that Wednesday test, that'd be more likely what you're going to get. So, also the calorimetry ones, like, sort of like your lab where you put a hot metal in a container of water and saw how much the temperature of the water went up. You should be able to do those calorimetry type problems with, phase changes as well. So you have the latent heat as well as the specific heat. Okay. And this is all going to be on recording, so feel free to check it out. It'll be posted tonight. So if you want to take notes off that, plus I did write quite a bit over here just to make sure you know. So any chapters other than 17 through probably at most 28. Any other chapters outside of that, even if they don't have an EC on it, they're extra credit. So don't worry about them. And I think I set the due dates to everything, to just about everything left to the 30th. I think I might even go ahead and set that to August 1, because that still gives me August the 2nd as the last day of classes, in case anybody needs some last minute extra credit that they would really like to improve their score with. So anyways, I'll probably be doing that too. Anything else?
Professor, I just wanted to let you know that I got the update on Canvas.
Oh, you did the announcement thing that's it? I'm not understanding what you mean by the update.
Oh, like, I think you were asking, like, you said you didn't know if you made an announcements on Canvas, it will get.
Oh, yeah, gotcha. That's what I thought you were talking about. So you did get it, Elron? That's cool.
I did not get it.
Oh, you did not? Oh, that stinks. So, okay, well, it didn't go out, but y'all can check. You know where, if you look up at the top left side of Canvas, you'll actually see, my lab and mastering modules, but one of them actually says announcements. If you click there, you'll see the top announcements, the most recent one. But that's good for me to know. I really all this time thought like
I got the notification for it.
You did? Okay,
Yeah.
cool. Someone did. That makes me feel better. I thought it was supposed to be like that. It might
If
just
you
be
have Canvas notifications on your phone, it'll send it to you.
Oh, okay, that's what it is. So yours got it that way as opposed to going to your CCC email.
Yeah.
Okay. Yeah, my Canvas app stopped working. So I probably would have known it if I was continuing to use it, but it stopped working on my Apple phone. So I should say it stopped working as an instructor on my Apple phone. I couldn't go and do my instructor stuff on it, so it wasn't much help for me. Okay, it looks like I got that. Oh yeah. Thanks for posting that. This is the actual announcement Nora posted for me. Yes, thank you. So that's in the.
Making sure that's the right one.
Yep, that's the one.
Okay.
So yeah, that's cool. Thanks for posting that, Nora.
That's fine.
Anybody else? All right, guys, look, I'm here for you and I'm here to help you, and I'm not trying to destroy your life or your career. So if you're stressed out, I get it. I knew you were going to be stressed out. That's why I made sure I hedged my bets a little bit when I suggested chapter 25 would be in there. So yeah, we're just chillax. And I'm sure Kevin's going to do the same thing, even though you've got this cool project going on that might be stressing you out. Kevin's not going to let you get a bad grade because of the complexity of the model and basically the project that you're working on. So he'll take care of you there. I have 100% faith in that. He's a very student-centered instructor. We're lucky to have him, that sort of thing. So between him and me, you'll be treated right. Don't worry. And that's why I try to get everything done at least a whole class day before the end of classes. That way you can say, hey, Mr. Younger, there's an error on my grade such and such, or chapter 8 didn't show, or in your case, say chapter 23 didn't show up the correct grade in your grade book. So make sure you keep an eye on that stuff, and let me know if you have anything. And by the way, for this last home stretch, there's 2 weeks between now and the final exam. So for that home stretch, it might be best if you text me as opposed to email me, because I get a ton of emails right now. But remember to include your first and last name, and whether you're in 241, 242, and whether you're in the night class, which is you guys, or the day class, which is the other people. Okay, so as long as I got that 2/3 pieces of information, then it should be good. But yeah, text me directly. Don't waste any time trying to do it otherwise. And just in case you don't have your syllabus anymore, which I hope you do, it's still on the page. I'll send this in message or chat form. Do not say it out loud, because this is going on the interwebs. So I don't want to start getting random calls from people in foreign countries and whatnot. So there's my phone number. Again, you guys can text me. I usually try to respond on those immediately, or I'll just say something like, hold on, I'll check that. So, all right. Well, when we last talked, I had worked a couple rough looking capacitor problems, and hopefully you found a buttload more of them to look at so that you can work through that. That type of problem that I work with the complex arrangement of capacitors is definitely the sort of thing that it pops up on a test. Maybe not, that was a 2-part problem. The first part's a whole standing problem all by itself, which is find the equivalent capacitance of those capacitors. And then there's a whole other part find the charge on each capacitor and the voltage on each capacitor. That, if I had that on a test, it would be two entirely separate questions. But they, as in that form, they're perfectly valid for this test on Wednesday. Okay. And of course, I've been teaching you about the paradigm. Now we've gone plenty far, so you should be able to start off with either Coulomb's law, hopefully not, or Gauss's law, hopefully, and find out electric field for some distribution of charges that have a opposite and charged side and a other charge as well. So in other words, capacitor type things, which would be concentric cylinders, concentric spheres, or parallel plates, stuff like that. Those all have capacitance. So you should be able to use Gauss's law or Coulomb's law to figure out the electric field between the positive part and the negative part. Then use V equals a negative integral at E dot dl to calculate the voltage difference from the small one, or from the negative one to the positive one. And then use C equals Q over V to compute the actual capacitance. That's that big paradigm that I said you got to, so make sure you can do that. All right, let's get started. So first off, as I said, we were talking about those capacitors. Then I even showed you this neat example that's not unlike what your book does, which is where you take a battery, you put two capacitors in parallel and have them driven by the battery. The battery sends a certain amount of charge out. Part of that charge goes to C1 and the other part goes to C2. And then once it's fully charged, you disconnect the battery, which means charge can't leave, and you carefully snip the connection between the two capacitors, flip them around, and then stick them back together. And they wanted you to find the new charges as well as the old charges, and the new voltage as well as, you know, the old voltage, which they'd already given you. So that was what we did last time. Now I want to handle some other stuff, one of which is this. It turns out that just like when I quote unquote derived Gauss's law for you guys, what I did was I introduced the idea of electric flux, which is the integral of E dot dA, right? And for Gauss's law, it was the integral of a closed surface. So it had a clear inside and outside that you couldn't get from the outside to the inside without crossing one of the surfaces, or you couldn't get from the inside to the outside without crossing one of the surfaces. That is what Gauss's law applies to. And what I did was I calculated that flux for a closed surface that happened to be a sphere around a point charge, or even it might have been I might have even called it just a spherical charge distribution. And in that case, when I calculated the flux, I got the total charge enclosed divided by epsilon naught. And even though I did that for a special case, that turns out to be exactly the right Gauss's law. Okay, so I'm getting ready to do the same thing with energy, where I'm going to choose a highly specific example and put it in more generic terms. And ultimately, I will get the right answer for that one as well, even though it's just for a special case. So just as a background, I wanted to give you that. So let's start off by sharing the screen. Okay. This is not where I want to, hold on a second. Okay, that's where I want it, yes. So I'm sharing the screen right about, guess that's it. Yes, that's it. Okay, so I'm sharing the screen right now, and your book does a derivation. There's a couple ways you could do it. Like your book does W equals, actually, let me not write that in red. Your book writes W is equal to the integral of V dq, but you could also write work is equal to the integral of Q dV. Both of those are acceptable. Either way, what you end up getting is the total work done in charging a capacitor is equivalent to the potential energy of the capacitor. And what we find is the potential energy of a capacitor is 1/2 CV squared. Now, if I employ the equation C equals Q over V, then I can use that expression, which, by the way, came technically from integrating this one.
Sorry, Professor. Are you sharing your screen?
Yeah, it's not showing for y'all? Yeah, it's showing on mine. Okay, I must have hit the wrong thing. Hold on. Thanks for letting me know. Yeah, this is, I think it's stop mirroring. Some reason it went right to my screen on my computer, but not to you guys. Oh, it looks like I might not have hit the word share. I hit the button that said share, but there's another button that says share after it. That might be where I screwed up. Yes, there it is. Yeah, it was just named Williams iMac. Now it's Zoom Williams iMac. So that's the one. I was noticing something was weird. I thought it wasn't going to work, but yes. Yeah, it should come up any minute now. Yep, there it is. Thanks for letting me know. So yeah, you can use work equals the integral of VdQ as I have written in the left there. Or you can have work equals the integral of QdV, which is the second one I have written. And if you, for instance, want to choose that second one, you could replace Q with CV. And C is a constant, so you pull that out and you have the integral of V dV, which is 1/2 V squared. And now you see why I got the U equals 1/2 CV squared. That's where that came from. If you did the first integral, that one actually would give you a different case. In that case, you're going to get V is equal to Q over C. So you'd say Q dQ over C. The 1 over C comes out. And of course, the integral of Q dQ is 1/2 Q squared. So you get 1/2 Q squared over D squared. I mean, over C squared. So you can also do that by replacing the C in here, for instance, with Q. And in that case, if you replace the C with Q over V, you'd get 1/2. And then C is going to be Q over V. So one of those V's are going to cancel out and just leave a Q V like that, because it would have been Q over C, or excuse me, Q over C is Q over V. So that would have been Q over V. And then that times V squared gives you 1/2 QV squared. Or you can also eliminate V by solving 1/2 CV squared there for solving C equals Q over V for V in that, and then plug that in the other side. If I do that, V is Q over C. And when I square it, I'll get Q squared over C squared times 1/2 C, which is just Q squared over 2C. So those are 3 different ways you could write energy. And that is technically the energy stored in a capacitor. Okay. Now I'm going to tell you that in reality, what has happened here is the energy is stored in a capacitor specifically because in the capacitor, there exists a electric field, and that electric field is what's made with the energy that happened. And for that reason, you have some energy just by charging up a capacitor. It holds energy for you. Your book has some simple examples like the flash cube one. You should definitely look at that. I thought that was too simple for me to work for you guys. But now let's take, for instance, this U equals 1/2 CV squared. And I'm going to do calculate for the special case of a capacitor exactly what U is. And that's going to give me the right answer, even though the right full general solution. So let's start with that. So I say U is equal to 1/2 CV squared. But we know, for instance, that C for a capacitor is equal to epsilon 0 A over V, the voltage. Okay, so I can put in 1/2 epsilon 0 A divided by the voltage. Now I need the voltage squared, but we also know, for instance, that V is equal to the electric field times D. Now remember, this expression right here is only true for E equals a constant. And that's what we found with the capacitor, is that the electric field in the capacitor is essentially a constant. It doesn't depend on time or X or Y or Z. So I can now replace that V with E times D. Okay. Oh, I wrote epsilon 0 A over V. That's not right. Let's fix that real quick. Hold on. That's supposed to be, everybody knows what that's supposed to be, right? What's supposed to be down here instead of V?
ED.
Yeah, it's actually should just be D, but yes, it's the formula, Jiminy, The formula for a parallel plate capacitor is in fact epsilon 0 A over D. So here's A and here's D. Now the V is supposed to be E D. So this, when I square it, makes it E squared D squared. That's kind of neat because now I can write it as 1/2 epsilon 0 E squared. Now I have just A times D. And if you take a picture or at least imagine an image of a parallel plate capacitor in 3 dimensions, let's say this is it, then what you'll find is this distance right here is the D we were talking about, and this area is A, as is this area. So I think you can see that in fact the AD that we have here is actually just the volume inside the capacitor. Everybody see that? Remember, if you multiply an area times, and this is part of the theorems of Pappus that you should have learned in calculus, but the theorems of Pappus basically say if you take they call it like a right prism. In other words, an object that has a constant cross section. Now, if you take the length that that cross section has to go through to get from one end to the other, and multiply it by that, then that is the actual volume. So taking A and multiplying it by D is in fact finding the volume between the two parallel plates. So the reason why I put that is because now I can divide both sides by AD and I'll get this smaller quantity, lowercase u, which equals energy density. Which of course would be in joules per cubic meter. Well, that's going to be 1/2 epsilon 0 E squared. Okay. And of course, that also means it is the big U divided by the volume, which volume is equal to A times D. Okay, so this is the expression that I was shooting for. And as I told you, it is in fact the right answer. In other words, this is true in reality, period. Even though I derived it for a very specific case, a parallel plate capacitor, it is the right answer. And that's very interesting because this is something that you're going to see, not unlike when we saw for the harmonic oscillator. Last semester, y'all talked about the harmonic oscillator, and we talked about it energy wise if you're in my class, but I'm sure everybody, no matter where you got it, talked about it as well. But basically, energy was sloshing back and forth between 1/2 K x squared, which is the potential energy of a mass on a spring compressed to distance x, plus 1/2 mv squared, which is the kinetic energy of the mass at any point. And of course, the total amount would be either equal to 1/2 K times A squared or 1/2 mv max squared. So that's sort of what you learned about harmonic oscillators. You realize that they bounce back and forth between these two versions of energy, so that when the spring is compressed to its maximum position, which is the amplitude, then all of the energy is in potential energy, and that's partly because the mass has come to a stop. Right? If it was still moving, then it has enough velocity and momentum to compress the spring a little more. So by definition, it has to be 1/2 Ka squared at that point, which does not include any kinetic energy. Or if you look at it when X is 0, in other words, when the mass is at the equilibrium position for the spring, you'll see all the energy at that point is just in kinetic energy, and that's the 1/2 mv max squared. So we know how things like that behave. Well, guess what? It turns out that the energy for a capacitor, inductor, resistor series, so for a RLC circuit, what we have is U is equal to 1/2 CV squared plus 1/2 LI squared. So you can see that's really beautiful, and it looks a lot like the harmonic oscillator equation, except now instead of position and velocity varying in time sinusoidally, the voltage V for the on the capacitor equation and the current I are switching back and forth, so that the energy goes back and forth between energy of magnetism, which is what the L is about, and energy of electric field, which is what the 1/2 CV squared is about. So that's kind of neat. And to finish that argument off, it turns out that U is also equal to 1/2 mu 0, which is a constant we're going to learn pretty soon, times B squared. So now we got these two expressions, 1/2 epsilon 0 E squared and 1/2 1/mu 0 B squared. So that again is showing you an exact parallel between magnetism and electricity, which at least in the RLC circuit includes parallels or analogies with the actual spring on a mass, or mass on a spring, excuse me. Does that make sense? All right, so these are some of the equations you'll have to use to solve some of the problems, but it's just basically a way of calculating the energy per unit volume. That's what those lowercase u's are. Now, the next thing I wanted to talk to you about is a bit of a conceptual example. So let's imagine we have a parallel plate capacitor and we charge it up. So here's our parallel plate capacitor. I want to say it's 3 of these long. Let's see, it goes back to there, goes back to here, back to here, and then back to here, and then back to here. So there's my parallel plate capacitor. Here's my wire that goes into it. Here's my wire that comes out of it. And in this case, what I'm going to say is I am going to take this and connect it with a battery. And that battery is going to have a voltage, let's call it just plain V0, say. So we'll say this is V0. And it's actually going to charge the capacitor up to a charge Q0. And Q0 can be related to C by C0 equals Q0 over V0. Okay. Now, this is also understood to be a distance D, and this is understood to be an area A. So we also know that C0 is equal to epsilon 0 A over D. Okay. So what happens what happens if once we have the capacitor charged? That means at a charge Q0, if we then disconnect the battery and then pull the plates apart to a separation of 3D. Okay, so that's what we're asking you. Anybody have any questions or about that? So I'm just taking a parallel plate capacitor, I connect it to a battery, I wait a few seconds, and then eventually the capacitor, if I actually took a positive, the red terminal of a voltmeter, and stuck it on the left plate, and the black terminal of the voltmeter and put it on the right plate, then that would read exactly V0. At that point, I then just disconnect the battery. And after the battery's been disconnected, here's what that means. It means that charge has nowhere to go. It's just a little wire sticking out of each end of the capacitor. So charge can't go anywhere. Charge can't change. That means the voltage, of course, is free to change, but I'm now going to take the plates and I'm going to grab those little pigtail strings and I'm pulling apart until the distance is 3 times as big as it was. And what I want you to know, answer is what happens to the charge. So here's the solution. So it turns out that one thing you consider, for instance, is the energy U is equal to 1/2 C V squared, which also happens to equal, remember I gave you other versions, it also happens to equal 1/2 Q squared over C. Now, the problem with using 1/2 CV squared is since I've removed the battery, the voltage can change all at once. So I don't want to use an equation with a variable that changes and I don't know what it's going to be, right? So I don't want to use that one. I might actually be able to use the other one, the 1/2 QV as well, but that one's got a V in it too. So there's another reason not to use it. So when this happens, what I know is I know that V changes, Q does not change, and the way your book put it, the way your book put it is that the charge has nowhere to go. Okay, so initially I had U zeros equal to 1/2 Q0 squared over epsilon 0 A over D, which becomes Q squared D over 2 epsilon 0 A. Okay. Now, after the fact, I am going to have, after separation, after pulling apart, after pulling farther apart, C goes to the new C, which is epsilon 0 A over, now it's going to be 3D. Okay. So what you can see happens in this case is U is now going to be 1/2, still Q0 because that can't change. And actually I can go ahead and subscript that Q0 if I wanted to there as well. 1/2 Q0, but now I have 3D here because the separation is now 3D. And I also have epsilon 0 times A, like that. None of that changed. So you might initially think, oh, okay, well, evidently the charges went up by a factor of 3 because this is in fact 3 times Q0 squared over 2 epsilon 0 A. Does that make sense to everyone? Oh, I forgot the D in here. So you see, hopefully that looks just like which also looks like that expression. So you see that the potential energy is actually increased by a factor of 3, and that's exactly right. That makes sense? Okay, so this is more stuff of making sense of how these equations work. So one of the key aspects you should learn is, hey, if I disconnect a object from a battery and it's just got 2 loose ends of wire, at least in a small time frame, whatever's happened to that's not going to change. In the case of a capacitance, it can store things for a long period of time, so the charge will not change because it's got nowhere to go. However, if you leave the battery connected and do stuff, then the voltage cannot change because the battery is going to lock the voltage down at like 12 volts or whatever. But the charge can change because the charge can be either forced into the battery or pulled out of the battery. Okay. So that was a nice conceptual example. It's sort of like 24-9. So I'll remind you that it's 24-9. And I'll say it's like that. You can see that when you look at it, you'll see I didn't change very much, but it's essentially the same problem. Looking at that, you can also look at 24-10, which is kind of neat, where it says the plates of a parallel plate capacitor have area A, separation X, and are connected to a battery with voltage V. While connected to the battery, so they haven't disconnected the battery, while connected to the battery, the plates are pulled apart until they're separated by a distance 3x. Okay, what are the initial and final energy stored in the capacitor? And B, how much work is required to pull the plates apart, assuming a slow constant speed? And then C, how much energy is exchanged with the battery? So I'm going to go ahead and use a whole nother page for this one, because otherwise it'd make it so I'd write so small and turn out to be crap. So the parallel plate capacitor initially, and this would be example 24-10. Okay, initially we have C equals epsilon 0 A over X. And V is the voltage of the battery, stays constant. Which implies Q initial, which I'll subscript both of those, by the way. I went back and subscripted the C to show that it's the initial one. I just put a subscripted O on it. So I'm now doing the O times this. So I'll get the Q is C times V. So in this case, it's going to be epsilon 0 A over X. And then I multiply that by V. And I didn't subscript the V on purpose. The V is, like I said, leave the battery connected. So that's what's going on. So if I want to then see what finally it is, we have C is now equal to epsilon 0 A over 3x, and V is the same constant, and Q, the new one, will be epsilon 0 A over 3x times V. Okay. So if I do U final minus U initial, which is delta U, that's going to be, I'll use the 1/2 CV squared version. So 1/2 CV squared minus 1/2 C0 V squared. I'm going to go ahead and pull out the 1/2 V squared because I know they're not going to change. And the C is just going to be, the final one is epsilon 0 A over X times 1/3. I could have written that less messy. Don't know why I didn't. So the 1/3 epsilon 0 a over x minus the original one, which was of course epsilon 0 a over x, like that. So basically we have 3/3 minus, or excuse me, 1/3 minus 3/3. Actually, let me see. I think I skipped something here. Oh yeah, times 1/2. Okay. So yeah, that works. So now when I compute this, you can see the 1/3 minus the 3/3, it gives me negative 2/3, but there's a 1/2 out in front. So I get negative epsilon 0 a v squared over 3x. Yeah, I think that's right. That looks good to me. Negative epsilon 0 a v squared over 3x. So everybody sees what happened. This quantity right here, for instance, became 1/3 minus 3/3, all of that times 1/2 v squared and times epsilon 0 a over x. This part right here, of course, just this is supposed to be 3/3. I wrote 3 seconds for some reason. So this would be negative 2/3, but then that negative 2/3 with the 2 here is basically going to make it 1/3. So that's where all that came from. So delta U is in fact this answer. Which I try to write it, box it off with a different color than the writing. So now part B, it said how much work is required to pull the plates apart. So that was part A. Part B, I'm going to say work is actually equal to, in this case, the integral of f dot dl. But I know that F is just Q times the electric field. So I can write it as the integral of Q times the electric field times DL. And I got rid of the dot product because the electric field is going to be exactly parallel to the work we do in pulling the two things apart. So the dot product's sort of irrelevant. Now I've got to figure out what is the charge and what is the actual voltage. Well, not so much the voltage, but yeah, what's going to make the electric field. So what I realize is, remember when we worked out for a infinitely large charged plate, we found that the electric field was sigma over 2 epsilon naught, and it always pointed away from the positively charged plate. So if you're above the plate and the plate's horizontal, then the force is upward, or the electric field is upward. And if you're below the plate, then the electric field is downward, right? But then we took 2 electric plates and put them side by side. One of them was negative and one of them was positive. That meant that between the 2 plates, they pointed in the same direction. The positive plate, for instance, would point this way, and the negative plate would point that way. So sigma over 2 epsilon naught plus sigma over 2 epsilon naught became just sigma over epsilon naught. So the main thing I'm trying to stress there is one plate makes half the electric field, and the other plate makes the other half. So as far as the electric field goes, we're going to say E is actually going to be V divided by 2L, where L is the separation between them at any time later. And so instead of just using X, I'm using L because I'm allowing that to change, whereas I acted like X was an actual physical quantity. Now Q is equal to CV. Again, that comes from the definition of capacitance, which is charge per unit voltage. So if I want to, I can say, all right, well, the Q in there is going to have to be equal to epsilon 0 a over, since I've switched to the terminology including L, I'm just going to put epsilon 0 a over L. That's what the capacitance is. And then the voltage is just V. So I can now say work is equal to the integral of QEdL becomes work equals the integral of epsilon 0A over L times V over 2L times DL, which again, we're not releasing the battery. We're not changing the area. So the epsilon 0, the A, and the V squared can all come out in front. Like that. Okay, and then I've just got the integral from x to 3x of, there's also a 2 under there. That'll help. Okay, yes. Also, it becomes dl over L squared. So that's the integral of L to the -2, which is -1 over L. So I'm going to say this is negative epsilon 0 A V squared over 2 times 1 over L evaluated from x to 3x. So this is going to be negative epsilon 0 A V squared over 2 times 1 over 3x minus 1 over x. Now I can make this right here 3 over 3x, and then I'll have a common denominator. And 1/3 x minus 3/3 x, good Lord, that's horrible. 1/3 x minus, dang it, minus 3/3 x is going to be negative 2/3 x. So ultimately I get negative epsilon 0 A V squared over 2 x times negative 2/3. In other words, I pulled that little x in the bottom out of the square brackets and put it out here. Now you can see those cancel out. So the work done in pulling it apart is obviously turns out to be a positive amount of work, and it's going to be epsilon 0 A V squared over 3x. So that's the work done in separating them. And you should realize that work should be a positive quantity, because when the plates are next to each other, remember, one plate's positive and the other plate's negative, so they're attractive. So it's going to take some force to pull them apart. That's why you're getting a positive amount of work. Now, the part C is they want to know how much work is required to pull the plates apart. That was part B. And then how much energy is exchanged with the battery. So what we know is for part C, we know that the work done in separating it is equal to the change in energy of the capacitor plus the change in energy of the battery. So that means the change in energy of the battery, which is what they're asking for, is equal to W minus delta U cap. Well, delta U cap is the same thing as this quantity up here. I just didn't subscript it cap until now. So now I can say delta U battery is equal to the work, which is 1/3 epsilon 0 A V squared over x, like that. And then I'm going to say minus a negative, and that negative is epsilon 0 A V squared over 3x. And minus a negative is the same thing as plus a positive. So we end up getting 2/3 which is 2 epsilon 0 a v squared over 3x is the energy of the battery. So that's delta U battery. In other words, what we did is added energy to the battery by basically applying work to the system to force the plates to come apart. That actually forced some of the charge to leave the plates and go into the battery, which is essentially what charging a battery is you're putting charges back in. So we've actually calculated the amount and everything. Anybody have any questions on that? All right. So what I'm going to do now is at 6:32, I'm going to go ahead and give you a 10-minute break. I'll be back at 6:42. Okay. And then we're going to go into the last two examples from this chapter and probably start into chapter 25, at least letting you know what the important parts of 25 are so you can get started on the homework. So make it 7:33. Excuse me, 6:43. Yeah, come back a whole hour. No, come back at 6:43. You'll be good. And I'm here if you have any questions. Check out my cool Homer Simpson shirt. I can't, man. Camera's fixing it. It's Homer Simpson wearing headphones. It's pretty awesome. Yeah, I got mad swag. My daughter just came back from traveling parts of Europe, but she went to Italy and Spain and a couple other places, and she came back with two shirts. Both of them were Simpsons related, and one of them had Bart holding up the Pisa, the Leaning Tower of Pisa. So my wardrobe is complete. It's hard drawing on a tablet, man. Not enough friction. All right, so it's 6:38. I guess we should go ahead and get back started. All right, so what we've been dealing with is basically just capacitors with air between the plates or even a vacuum, because it turns out that air actually has dielectric constant as well, but it's like in the fourth decimal place. So it's like 1.0002 or something like that. That's what the dielectric constant for air is. But it turns out you can actually make the capacitance increase by inserting a dielectric. And when you do that, what you get is, instead of just a parallel plate capacitor, which initially we know looked like this, like that, but now we can take and fill that space up with a dielectric that in most cases fills the whole space, but in principle you can still partially fill it if you want. And the dielectric constant for that particular material is just going to be K. And what we know that happens is C, 0 goes to C, which is in fact the dielectric constant times C0. So for a parallel plate capacitor, that means we now get K times epsilon 0 A over D, again, where D is this distance and A is that cross-sectional area. Okay, now that's particularly nice because one, putting that dielectric in there, you see that these plates are basically just positively and negatively charged plates, and obviously they're attracted to each other, so the two plates want to touch each other already, and you're going to try to make them as small as possible to fit them in whatever electronic device you have. So you're often going to take the two metal things and sort of roll them up very thinly. If you do that, you can imagine you're getting them so close together, what could possibly keep them apart? Well, that happens to be a dielectric. You can put a dielectric, which again, I tell you is a fancy word for insulator. You can put a dielectric in there, and that gives you structural stability so that you could keep the plates away from each other just by touching by accident. And not only that, it boosts the actual capacitance by the factor K, and it often has a breakdown voltage that's actually quite a bit bigger than the breakdown voltage of air. Remember, we found that the breakdown electric field strength, and I keep going back and forth between calling it voltage, but it's volts per meter, so it's not really fair to call it voltage. So the breakdown electric field for air is actually 3 times 10 to the 6 volts per meter. So if you have two pieces of metal, say one positively charged and the other one negatively charged, if the voltage difference between them is 3 million, then the air will ionize between those two plates. And if they're a meter or less apart, then the ionizing air will cause lightning to strike, basically coming from one plate and going to the other. So that's what's happening. But if you look, and I won't pull up this page. Well, I guess I can. I ain't going to show up for a second. I'm sure they're not going to get me. But I'll stop sharing this for just a second. And now I'm going to start sharing this other thing, which is this page. So start sharing that. So what I wanted you to see is the table of dielectrics. There's the expression I just finished telling you, that the capacitance is now kappa time, or K times C0. I used to use kappa. I swear that's what my physics teacher taught me when I first came into it, but no one's doing that anymore. They're just using K. So either I thought they were using kappa and I was wrong, or they were not using kappa, or they were and they just changed it. But anyways, air you can see has a dielectric constant. I actually said 1.0002. It's actually 1.0006, and it has a breakdown voltage of, or I should say, breakdown electric field of 3 million volts per meter. But you can see paraffin automatically gives you a factor of 2.2 capacitance and gives you a factor of basically 10 thirds, or about 3.33 times more capacitance. You can see some of these things get really crazy. For instance, you can talk about strontium titanate. That actually has a dielectric constant of 300. So you can increase the capacitance by a factor of 300 if you fill the space up with strontium strontium titanate. It's easy for me to say, right? But notice it's only a modest increase in the breakdown electric field, 8 times 10 to the 6 volts per meter. Now, sometimes we also, instead of wanting to talk about that, we can say C is also equal to epsilon A over D, where epsilon is equal to K time, or excuse me, epsilon is equal to K times epsilon 0, in which case you call this the permittivity of the material. And if I learn to spell, that's going to be awesome. So that's the permittivity of the dielectric. And in fact, your book goes so far as to say that expression we had before, if you want to find the electric or the energy stored in the electric field per unit volume, it's now going to become 1/2 epsilon E squared, or 1/2 K epsilon 0 E squared. So that's another expression that's helpful. All these are actually helpful. And now we're going to try to see what happens with that. Now, specifically what goes on is we'll discuss it at a microscopic level, and there's very specific equations you use. But right now, what I want to do is let's imagine an air-filled capacitor has a capacitance of, so here it is. This is going to be example 2411. So we have an air-filled capacitor. Has a C equal to C0. And that's going to be specifically with a separation of D, okay? And we're going to connect it to a battery. Of voltage V0, and acquires a charge Q0. With the battery still connected to the battery, or excuse me, with the capacitor still connected to the battery, I'm going to insert a dielectric. So with the battery connected, I insert a dielectric K equals 4. And it fills the space. What I want to know is, will Q increase, decrease, or stay the same? So what will happen to Q? That's the big question. Okay. Well, what we know is that C 0 is equal to epsilon 0 A 0, or excuse me, just plain A over D. So I'm going to erase that sub-0 there. Epsilon 0 A over D. I didn't put did I write D in there somewhere? Yes, I did. Okay. And I'll put that off in quotation marks, put this off in quotation marks, and put this off in quotation marks. Okay. Now, when I leave the battery connected, that means the voltage stays the same, but the actual charge can actually change, because charge can flow back into the actual battery or it can flow out. But the main thing is the voltage from C equals Q over V. The voltage is equal to Q over C. Okay. And that's going to stay constant.
Professor, I don't think we can see what you're writing. We just see the textbook currently.
Did I do it again? Oh, no, that's
Yeah.
right. Stop it. Thank you. Thanks.
You're
I've been writing off a storm over here. I've just been doing my own little thing.
I've been following, but I haven't seen you writing.
Well, I'm glad you're following. That's the main thing. All right, here we go. Crack me up. All right. It says it's coming. You know, there's always a delay. Still coming. Well, luckily, most of the stuff, actually, no, you didn't see any of that I wrote. Holy crap. Yeah, I remember it. So this is what I wrote. So notice on the top left, we see a capacitor with cross-sectional area A, or plate area A, separation D. And what we're saying is, when I add a dielectric constant, a dielectric that has a dielectric constant K, the C becomes K times C0, which we can write as K times epsilon 0 times A over D if it's a parallel plate. And I mentioned the breakdown electric field strength is 3 times 10 to the 6 volts per meter for air. And then I said some people also, instead of using K, they'll actually just replace the epsilon 0 with an epsilon, and epsilon is actually K times epsilon 0. So that's the permittivity of the dielectric. Okay, so they can use that. And notice over here that the electric field and the energy stored in it can be expressed that way as well. So if you're asked to actually calculate the energy within an electric field that happens to be permeating through a dielectric, i.e. an insulator, you have to figure out what the electric field is in there, so you can put the E squared part, but you're also going to change the epsilon 0 to K times epsilon 0, or just to epsilon. Okay. So that's what I was getting at. So now we're talking about this example 2411. It says an air-filled capacitor, capacitance is C0, with a separation of D, and an area A is connected to a battery, V equals V0, and acquires a charge Q0. With the batteries connected, I insert a dielectric with a dielectric constant of 4, and it fills the space. In other words, it spans from one plate to the next, and from top edge of the plates to the bottom edge, and from the front edge of the plates to the back edge. It fills the whole space. Okay. What will happen to Q? Well, what we know is the voltage isn't going to change, but the capacitance definitely is going to change, and the charge can change because it's got a wire connecting it to the battery. But V doesn't change. Thanks for letting me know I wasn't copying to you, so that that came out pretty helpful. So what we can now say is that Q0 over C0 has to equal the new Q over the new C. Okay. So if the new C is in fact K times C0, then you get Q0 over C0 is equal to Q over K C0. From that, you can see that C0 is going to cancel out, and we can find that Q, I should probably stick to the blue. We're going to find that Q now is equal to K times Q0. And that's the main result we're supposed to get. Okay. So when you actually stuff a capacitor into a parallel plate capacitor, that evidently increases the number of charges Q that will string up on each side of the plate by an amount K. Any questions on that? That's sort of a conceptual problem, but again, it's something that you want to know. The two rules are voltage doesn't change if you keep it connected to a battery. And the second one is if you disconnect it from a battery, then the charge will not change. Okay. So now let's look at the example 24, essentially the example 2412. I think that's what, yes. Example 2412. Basically says, suppose an air-filled capacitor, the same one we were just doing, is charged to Q0 and then disconnected from the battery V0. Next, that same dielectric is inserted between the plates. Will Q, C, or V change? So we're now doing the same stuff. C0, A0, V0. Notice I've got this now, V0 and D. And then we're going to disconnect the battery. And insert the dielectric. Okay. And all they're asking is whether will Q, C, or V change. Okay. Well, in this case, we know V can definitely change. So I'm going to say solution. Battery disconnected. Implies V will change. Will slash can change. And the capacitance will change from C0 to K times C0. And Q, which technically is Q0. Oops, that's the other thing I forgot to put up here. Let's put it up here real quick. Q0. Q will change. Q can't change. Sorry, I don't know why I even wrote that. Will not change. And that's because, again, it's just a loose wire sticking out of each side of the capacitor, and it's not going to have any ability to go anywhere except over an extremely large period of time. You know, ionized air could interact with it, or polarized air could interact with it and steal some current, some charges over time, but in general it won't. In this case, since C is equal to Q over V, and Q can't change, then Q equals a constant. Actually, I said, yeah, it can't change. Q equals a constant, and that constant equals C0 V0, which is also equal to K C0 times the new V. So I think what you can see now is that the new V will become V0 over K, because that's what happens when these C's cancel out. I meant to do red on that. Okay. And that's it. That's the actual result. So V definitely changes. In fact, inserting a dielectric reduces the voltage from V0 to V0 over K. The C goes from C0 to C, which equals K times C0. And Q stays the same. Again, just another conceptual question that you sort of have to make some sense of by using that equation C equals Q over V. Sometimes we use U equals 1/2 CV squared. All depends on what you're working on. So any questions on that? All right, now the whole reason we were really doing that was because you can see that V0 changes from V0 to V equals V0 over K. And you might think, is what actually did that? Well, it couldn't be the charge because the battery was disconnected. But what we found is that the electric field within the dielectric will be the new V divided by the D, which is V0 over K. And from that, we can infer that V equals V0 over K suggests that E, at least in the dielectric, is equal to E0, which is the electric field it had without the dielectric, divided by K. Okay. So there's two major experiments that they did that were actually took a lot of work. And basically what they did was take a container, or excuse me, take a parallel plate capacitor, and you leave it connected to a battery so that the voltage can't change. And then if you very carefully insert a dielectric in there, then the capacitance will go up by a factor of K, excuse me. But since it's connected to a battery, the voltage can't change. So in fact, what happens is it summons more charge so that the charge goes from Q0 to K times Q0. Now, if you did the other way where you charge it up to Q0 and then you disconnect the battery and slide a dielectric in there, again, the capacitance, which is Q over V, becomes K times the C0. But this time the voltage can change, but the charge can't. So the charge stays the same. And the only way you can account for that is V0 decreasing to a factor V0 over K. And that is evidently what happens with the electric field, because remember, the electric field can be integrated over the thickness of the distance between the plates. It can be integrated across that, and you'll just get the electric field times the distance. That's the only thing it depends on. The electric field is an actual constant between the plates. So you then conclude that the voltage decreases by a factor of K specifically because the electric field decreases by a factor of K. And this equation, in fact, is true whenever a dielectric is inserted even partially. In other words, if I just stick one that's not thick enough to reach from one plate to the other, the electric field in the dielectric is going to be E0 over K in the dielectric. It'll just be E0 outside of it, but inside it'll be E0 over K, even if the dielectric doesn't fill the whole space. So now let's look at another example. So now that we have those experimental results and we have this knowledge of how capacitors behave, we can try working an example. So let's say a parallel plate capacitor. I don't want to write write in red. I want to write in black. And this is essentially example 2413. A parallel plate capacitor filled with a dielectric K equals 4.0 is connected to a, well, I don't like that either, to a 200 volt battery. After the capacitor is charged, we disconnect the battery. Okay. And I want to A, if A is equal to 8.0 meters squared and D is equal to 8.0 millimeters, then find C. Let's also find the charge Q. And let's also find the electric field strength. And U. Part B, we then remove the dielectric. We then remove the dielectric, and of course, this is a very difficult task. You can imagine the dielectric is literally touching the left plate, the right plate, and you're trying to pull it out. You don't want to take any of the charge with you, all that good stuff. So now what we'd like to find is the same thing. Find what I'll call C prime, which is a new capacitance, E prime, which is the new electric field, V prime, and I guess, yeah, we did the electric field. Oh, Q, we want the new Q and the new electric field strength. And then we already did that. Let's see. Oh, the new energy. That's what I want to do. So that's what we're looking for. So let's do solution. Everybody understand the problem now? So we have a parallel plate capacitor. It's got a dielectric in it, and its dielectric constant is K. And we first want to calculate the capacitance, the charge, and the electric field. So let's start off with part A. So C is equal to K epsilon 0 A over D. In this case, the K is 4.0. The A is 8.0, and they were nice enough to give us it in square meters. And I was goofy enough to write it at 2 levels, so it looks like a fraction that didn't happen. And then over D, which is 8.0 times 10 to the negative 3rd meters, and then times epsilon 0, which is 8.85 times 10 to the negative 12th coulomb squared per Newton meter squared. So the capacitance should be equal to 4 times 8 times 8.85 e to the negative 1, 2. And then divided by 8 e to the negative 3. Make sure I got everything right there. 4 times 8 times 8.85 10 to the negative 12 divided by 8 times 10 to the negative 3. Looks like I put everything in. So this is 354 times 10 to the negative, or 3.54 times 10 to the negative 8 farads, which of course you could divide that multiplier by 10 and that'd make it 10 to the negative 9. And then you could divide or multiply the 3.54 by 10, and that would make it equal to the original quantity. So it'd be 35.4 picofarads. So that's also another way you could do it. Or excuse me, nanofarads, not pico. Okay, so those are all correct answers. Now what we want to know is Q. Well, C is equal to Q over V. So that means Q is equal to CV. So that's 3.54 times 10 to the negative 8 farads times the voltage, which in this case was 200 volts. That should be 3 sig figs. Technically speaking, we should have only had 2 sig figs on this number, so I'll put a underline there. So let's multiply this by 200, which obviously you don't really have to do. It's 7.06 times 10 to the, actually just 7.06 times 10 to the 2, which would be 7.06 times 10 to the negative 6. So I get, oh, I said 6, 7.08 times 10 to the negative 6 coulombs. So it's on the order of microcoulombs. So I'll write Q is equal to 7.08 times 10 to the negative 6 coulombs. Again, like I said, you could have written that as microcoulombs, but we have that. Now, the next thing we want to know is the electric field. And we can take the electric field and realize that E between the plates of a parallel plate capacitor is sigma over epsilon naught if we wanted to. But we could also take and multiply or divide V by the distance. Either one of those would work. So if I do that second one, I'm going to say 200 volts divided by 8.0 times 10 to the negative 3 meters. So 200 divided by 8 e to the negative 3 gives me 25.0 kilovolts per meter. So you can test that for yourself if you want to. You could take the sigma, which is gotten by taking the Q and divide it by A. So I could take 7.08 times 10 to the negative 6, and I divide that by 8 square meters. That gives me 8.85 times 10 to the negative 7th. That's coulombs per square meter. Now I'm going to divide that by 8.85 e to the negative 12. And that's going to give me, that should give me the same result. Sigma, is that right in the right number? Oh, no, I put in the wrong number, no wonder. Okay. But yeah, either one of those versions should work. I've got that. Oh, I need the U. So U is equal to 1/2 CV squared if I want. So I'll say U. That's the one I normally use because it's the easiest to remember because it looks like all the other ones. So this is 3.54 times 10 to the negative 8 farads times V squared, which is 200 volts squared. I'm treating that as if it's 3 sig figs. So 0.5 times 3.54 e to the negative 8 times 200 squared. This gives me 7.08 times 10 to the negative 4th joules. And that is the energy stored before we pull out the dielectric. So part B, it says when we remove the dielectric, let's find out what it is. So that's what I'm going to do now. So C, the new one, C prime, just becomes C divided by K, because obviously the K is made the capacitance increase by a factor of K. Therefore, if we divide out that factor of K, it should give us the new capacitance. And that should, of course, be 3.54 times 10 to the negative 8 divided by 4. So 3.54 times 10 to the negative 8 divided by 4. That gives me 8.85 times 10 to the negative 9th farads. So you can see it went down. The other one was 35 nanofarads. Now we're looking at 8.85 nanofarads. Now we also want to know the new Q, but the battery's been disconnected. So Q prime is equal to Q is equal to 7.08 times 10 to the negative 6 coulombs. So that one didn't change, and I decided to go ahead and stick with the red letters for that one since it didn't change. And next we're going to find we can find the new voltage. So V is equal to V prime is equal to Q over C. So now I've got 7.08 times 10 to the negative 6 coulombs. And God, I made that bad. Times 10 to the negative 6 divided by the new C prime, which I should put there and there. And in this case, it is 8.85 times 10 to the negative 9th farads. And we're going to get 7.08 e to the negative 6 divided by 8.85 e to the negative 9. And that gives me instead 800 volts. And that's to be expected because remember, the voltage that we had with the capacitance was actually a smaller voltage. It had been basically decreased from the original by a factor of K because it's supposed to be V0 over K. So this does make sense that it's in fact 4 times larger than what it was with the battery connected. So we got that. We've got Q prime, C prime. Now we need the electric field. So the electric field, we could say E, here this, we could say E equals V over D. Let's stop erasing everything. E equals V over D. I could say that's going to be 800 volts divided by 4.0 times 10, or excuse me, it was 8.0. Times 10 to the negative 3rd meters. So if I take 800 and divide it by 8 e to the negative 3rd, I think you can see what's going to happen. That's going to give us 100,000. So 1.0 times 10 to the 5th volts per meter is the answer there. Does that make sense to everyone? All right, now all we're left with is I've done C prime, E prime, V prime, Q prime. Now I need U prime. So U prime, oops. U prime, I'm still going to use 1/2 C prime V prime squared. So that's going to be 1/2 times C prime was 8.85 times 10 to the negative 9th farads, and V is 800 volts squared. So I'm going to say 800 squared times 8.85 e to the negative 9 times 0.5. And that gives me 2.83 times 10 to the negative 123 joules. The original U was 7.08 times 10 to the negative 4th, considerably larger. We actually got considerably smaller in this case, and that too is to be expected. Any questions on that? Actually, is that right? Did I get smaller or did I get larger? When I have CD squared 3.54 to the negative 8 times 200 to the negative 4th. Oh yeah, it got larger. Sorry. Yeah, it should have gotten larger because the C got smaller, but the V got larger by a factor of K squared. So yeah, it should have been larger in the second case. Everybody understand what I'm saying there? The C, when we remove the dielectric, C goes down by a factor of K. So you would go down by a factor of 4, but V is going to go up by a factor of 4, and V is squared. So that's by a factor of 16 total. So 16 divided by 4 is 4. So this 2.83 times 10 to the negative 3rd should be 4 times larger than the energy initially. And that's exactly what we got, because 4 times 4 times 7.08 is 2.83. Any questions on that one? All right, so one last, I've been doing these conceptual problems. I got one more problem that has to be done with regards to dielectrics. But to do so, I want to introduce the idea of what happens at the molecular level. So when you have a parallel plate capacitor like this guy, say, and this, okay, if you have a dielectric in there, then the dielectric is, like I said, it's another word for an insulator. So the electrons are not so free to move around, but the individual molecules or the individual atoms can be polarized so that they become something sort of like this with a negative side and a plus side, and then this with a negative side and a plus side. Now, when you look at it that way, then you're thinking, hey, wait a second, this almost looks like a scenario in which there's an electric field due to the capacitor, and that's E0. But because all of these polarized molecules / atoms or whatever in here, some of these electric field lines will actually terminate. In other words, we know it's not going to completely cancel out the electric field, but maybe 1 over 20 atoms is going to cancel out electric field, because the way field lines work in the electric field world is the electric fields originate on positive charges and then die or disappear on negative charges. So this first one might have went through unscathed, but this next one, for instance, might have went right here and met its doom, because there's a negative and a positive right there, and then there's a negative and a positive right there, and then it picks back up itself. Oops. it picks another electric field coming out here. And then the next one, of course, can go all the way through. Then the next one's come to a stop like that. So what you end up getting is that it's almost as if when we take the capacitor and we just pretend like we can see through the dielectric, then what's really happening is we have an electric field, let's say, like this, that is E0, but because the dielectric is acting as if the left side is charged negative and the right side is charged positive, there exists another electric field which is the electric field in the dielectric. And I already told you what we're going to assume with that is that E in the dielectric is going to be the E0 divided by K. Okay, so that's one way we can interpret it, because that's really what's going to happen. You're going to polarize the individual molecules and atoms. They're going to act like an electric field pointing in the same way, in the opposite direction. And because that electric field's now gotten smaller, more charges are free to come over there and stuff like that. So we end up getting that the total electric field in a dielectric, E dielectric, is actually equal to the electric field due to just the capacitor minus the electric field induced. And what I mean induced, I mean that little bit of field that was caused by those charges on the dielectric. Well, that's all going to be equal to E0 over K. So ultimately, you can say that E induced, in other words, the electric field induced as a result of the dielectric, is equal to E0 times 1 minus 1 over K. Now, you can think about that as being a result in the electric field being weakened, but you can also think about it as a result where the charge was weakened, and you could say Q induced is equal to Q0 times 1 minus 1 over K. Or you could think about it as if the surface charge induced is equal to the initial surface charge induced times 1 minus 1 over K. Doesn't really matter, just one of those three, as long as you don't like end up having 3 factors of 1 minus 1 over K, or even 2 factors of 1 minus 1 over K, then you're golden. So that's the molecular behavior of the dielectric. Now, what we're going to do is use that result to actually solve a physics problem. So I'm going to switch pages again. And let's see. I'm afraid I might be running out of paper. Yeah, I got it. Okay, that's plenty. All right, so now we're going to do something like example 2414. So 2414, a parallel plate capacitor has an area. So a PP capacitor has A equal to 500 square centimeters, which I'll have to convert that later, and a separation L is equal to 3.00 millimeters. Okay. The capacitor is going to be charged to V0 is equal to 200 volts. And I'll put a decimal there so we can realize that that's supposed to be 3 sig figs, as is that, as is that. and then the battery is disconnected. Okay. Now a dielectric of K equals 4.00 is, well, I should say, with A equals 500 period centimeters squared, but its thickness is 1.50 millimeters. Okay. So now a dielectric is inserted. What I want to know is A, C0, in other words, the capacitance before I put the dielectric in there. B, Q0, again, before the dielectric is put in there. And C, I want to know the charge induced. So I want to say Q induced is equal to question mark. And of course, induced means it's after the dielectric was inserted. And then I want to do D, the electric field in the space between the plates, but not in the dielectric. So I'll call that E0 equals question mark. And E, I want to know E in the dielectric equals question mark. I think that's just about it. Let's see if there's anything else. Oh, F, I want to know this new V afterwards. And G, I want to know the new capacitance. In other words, if it was a full thickness capacitor, dielectric in the capacitor, then the capacitance would go up by a factor of 4. What's the factor going to be since it only fills up half the space? That's the big question here. Okay, so first thing I know, C is equal to Q over V. That's something I have to know. For a parallel plate capacitor, I also have to know epsilon 0 A over D, that sort of stuff. So for part A, I want to figure out what the capacitance is. So for part A, I want to say C0 is equal to epsilon 0 A over D, which is going to be 8.85 times 10 to the negative 12th coulomb squared per Newton meter squared, times the area, which is, no, not that, it's 500. 500 centimeters squared times 100 centimeters in the bottom with 1 meter on top is 1. But I have centimeters squared, so I have to square that. And then I'm going to divide all of this by D, or in this case, we call it L. So let me change that so y'all don't get confused, because otherwise you might be thinking, oh, he means the D that he said for the thickness of the dielectric, and that wasn't it at all. So the L in this case is going to be 3.00 times 10 to the negative 3rd meters. So I'm going to take the 500, I'm going to divide it by 10,000. And that gives me 0.05 times 8.85 e to the negative 12th. And then I'm going to divide all that by 3 e to the negative third. And that gives me 1.475 times 10 to the negative 10th farads. Now I should only have 3 sig figs, so this 5 is an extra sig fig. And in fact, that's not written very clearly, so let me make that a little better. Okay, so that's the new capacitance. We've got that. I'll just underline it to make it a little less. Well, I think I can box that off. Part B, I want to know Q0. Well, Q0 should equal C0 times V0, which is equal to 1.475 times 10 to the negative 10th farads times the voltage, which is 200 volts, which of course you can do that math in your head, but it's 2.950 with an underline times 10 to the negative 8th. And that's coulombs. Now we want to know C, which is Q induced. So for part C, Q induced is equal to Q0 times 1 minus 1 over K. So that's going to be 2.950 times 10 to the negative 8 coulombs times 1 minus 1 over 4.00. So that's 0.75 because 1 minus 1/4 is 3/4. And that gives me 2.213 times 10 to the negative 8 coulombs. So notice, of course, it has to be this way. You can see by the formula. But yeah, the induced charge is less than the charge that was originally on the capacitor. That's key. Part C, that was part C. Part D is the electric field. So for the electric field, we're going to say part E. I got to get back to red. Hold on. So we want to know E0 in this case. When we go to do E0 in part E, what we're going to use is either sigma over epsilon naught, like that. That works fine. Or we could possibly use the V over L thing, but we don't know the voltage yet. So pretty much, I think we're pretty much stuck using this. So what I'm going to do is I'm going to take the charge that I just calculated, not the Q induced, but the other one, and I'm going to take that and divide it by epsilon 0 times A, because sigma is Q over A. So I'm going to say 2.950 times 10 to the negative 8 coulombs divided by 0.0500 cubic or square meters, excuse me. So that right there is my sigma, and hopefully that's helping you make sense of the sigma a little better. I know students are still having problems understanding what that is. And then divide it by 8.85 times 10 to the negative 12th coulomb squared per Newton meter squared. So I'm going to take this 2.95 e to the negative 8. I'm going to divide that by 0.05. And that gives me 5.9 times 10 to the negative 7th coulombs per meter squared divided by 8.85 ... I just wanted to show you one extra step so that ED is equal to that number divided by 8.85 e to the negative 12th. And that gives me 6.67 actually I'll say 6.667 times 10 to the 4 volts per meter, which you can also realize is 66.67 kilovolts per meter. Any questions on that part? Now I need to know the electric field in the dielectric. Remember, that was the equation that I told you was true even when the dielectric partially fills. See right here, true whenever a dielectric is inserted, even partially. So the electric field in the dielectric is just E0 over K. So I'm going to do that now and say part F E, this is supposed to be E0, in case you're trying to understand, but ED is equal to E0 over K, which equals 6.667 times 10 to the 4th volts per meter over 4.00. And that gives me 1.667 times 10 to the 4 volts per meter again. So you can see that one's considerably smaller, but it is still around the same order of magnitude. Now part G. Part G is us wanting the voltage. So what the voltage is going to be is it's going to be E0 times the thickness of the the separation between the plates minus the thickness of the dielectric. So it's going to be L minus D times E0 plus the dielectric times the D. In other words, when you actually make the parallel plate capacitor, which I can draw right here, say, the dielectric is this little part and ED is in here, but in here and here is E0, all of which is constant. So when you go to do the integral of E dot dl, you're just going to get E times whatever length is not in the dielectric plus ED times whatever length is in the dielectric. So in both cases, it's 1.5. So I'm going to say E0, which is 6.667 times 10 to the 4th times 1.5 e to the -3 plus 1.667 e to the 4th times 1.5 e to the -3. And of course it gave me a syntax error because I put a space in by accident. You aggravate me. 6.667 e to the 4th times 1.5 e to the -3 plus 1.667 e to the 4th times 1.5 e to the -3. That gave me 125.01. Don't know why I'm writing in green all of a sudden. Actually, I do, but still aggravates me. 125.01 volts is the actual voltage. What we called V prime before. I know we just called it V, so I'll go with that. And then H is where they're wanting to know C equals Q over V. So that's really the essence of it. I'm just going to take the Q, the 2.95 times 10 to the -8 coulombs, and I'm going to divide it by the 125.01 volts. 2.95 e to the -8 divided by 125, and that gives me 2.360 times 10 to the -10th farads. So we had 1.475 times 10 to the -10th. Now we got 2.365 or 2.360 divided by 1.475. That gives me 1.6. So it filled up half the space and gave me less than half of the spring of the dielectric constant. So that's how that behaves. It doesn't behave as exactly half or half squared or anything like that. It's just a long, drawn out process to work out what happens. So that is it. Oh, and we ran over class time, didn't we? No, 7:50 is what we're supposed to go to, right? Yeah. All right. So any questions on that? Okay, so that was the last thing for chapter 24. I just want to make sure you guys knew how to do that. You've been working on your homeworks most of the time. I know the last time I looked at it, I think the homework was a couple parts were pretty taxing, but other than that, it was pretty straightforward. This problem right here is the type of problem that could appear like on a final exam or something like that. I'm almost 100% certain it will not be on the test coming up Wednesday. Okay. I'm more interested, like I said, in your new paradigm where you take the Gauss's law, find the electric field, take the delta V equals the integral of E dot dl to find the voltage, and then you C equals Q over V to calculate the capacitance. I'm interested in your ability to do an integral to calculate, for instance, the electric field due to an infinitely long straight wire. So that was like the first calculus problem we did in chapter 21. That's a very fair thing, but that's again, that's sort of the probably one of the most difficult problems you'll do this semester. We're going to go to Ampere's law by next week, and when we do that, that'll be an easier version of the Biot-Savart law. So it'll be sort of a parallel to Gauss's law. But anyways, that's what that is about. Let me stop sharing the screen. These will all be posted. These notes are posted usually within 20 minutes after the class. What I thought I'd do now is go ahead and show you what's relevant to you regarding chapter 25, so you can at least get started on that. Chapter 25 is not a hard chapter. Let me show you what I mean by that. I'm going to go over here. You are looking at the book with me. And you can go to chapter 25. Now, one thing I want to tell you is all it takes to make a battery is two dissimilar metals, and you put them in a solution that has the ability to become ionic. So distilled water would not be a good choice, but just regular water would be good. Lemonade would be good. Acid would be good. A base would be good. In fact, that's the difference. An alkaline battery is basically dissimilar metals in a base, and acidic battery would be dissimilar metals in an acid. But what I do, and this is the original drawing here, you can see they're marked ZA, ZA. If I remember correctly, that's supposed to be zinc and aluminum. What I would do is I'd imagine taking like a zinc washer, and you put it in a little pill bottle, like a prescription bottle. And maybe before you throw the zinc washer in there, you might solder a wire into it so the wire comes out of the bottle for you to have access to. And then you lay that in the bottom, and then I would lay a piece of gauze or something to separate direct contact between it and the next metal. And then I drop in there a piece of, let's say, copper, like a penny. Okay, that's copper plated, of course, but it's close enough. So we have zinc under it, then a little bit of gauze, and then a penny, and maybe that penny has another wire actually soldered to it. And if we then filled it with like lemonade or lemon juice or anything like that, Gatorade would work. You could actually measure the voltage between those two wires, and you'd probably get on the order of 0.2 or 0.4 volts, something like that. Now, if we did the same process, take that wire off the top, put a gauze on it, put another piece of zinc on that, put another piece of gauze, put another piece of copper on that, and then solder it to that copper. If it was 0.2 before, it will now be 0.4. If you add another 2 more, it might jump up to 0.6. And it mostly keeps up that rate, but it starts to decline a little bit each step. But the more stacks you put on it, the higher the voltage will be. And you can easily get enough voltage to, say, light a diode or something like that. Now, what I do for my Port Discover stuff, it's been a while since I've seen them anyways, but when I did do it for kids, what I do is either buy an apple, but you can literally use an apple, a lemon, an orange, a potato, just about anything. And what I do is I take a big, like, number 10 wire, which is made of copper, and jab it inside of, say, the lemon. And then on the other side, take a galvanized nail and jab that in the other side. And that would give me usually about 0.6 or 0.7 volts, which is enough to turn on the diode again. But if I wanted more, then I could just connect them head to tail. So I'd take the zinc in and connect it to the copper end of the other lemon, and then the zinc into that, attach it to the copper end of the next lemon, and so on and so forth, and just span the whole thing. And you could actually pretty quickly make a voltage source that's plenty high. So that's something you need to understand about how batteries are made. You should also understand that a real battery is essentially an ideal battery, which is marked by the little symbol for a battery, which is basically one short line and one long line. And if you put a small resistance in series with it and you sort of pretend like that's a real resistor that's going to increase over time, then you have a good model for a real battery. So it's not uncommon to talk about a battery having an internal resistance of 1 ohm or a half a ohm. That's the way we treat it. And of course, as this drawing shows you, that's how you wire, for instance, a light bulb. The little dull gray thing at the very bottom of the bulb is actually normally lead, and it's lead on purpose because you can just touch it with a soldering iron and it will instantly melt. So you can easily solder a wire to it. And then there's like a bright, shiny piece of plastic that isolates it from the threads. The threads are the other terminal. So you literally have one wire that goes to the bottom and then one wire that goes to the threads. And it doesn't matter which way the current goes. It could come in the threads or it could come in the bottom, but it's going to go through this tungsten. That tungsten is going to carry so much current that it's going to get hot, and hot enough to basically exceed a couple thousand degrees. And therefore the radiation put out by it will come out in the visible spectrum, and that makes it incandescent light. The main thing to remember about batteries is you have to actually connect them in a circuit. So it has to be able to imagine conventional current as positive charges leaving the long side of the battery diagram, or the plus side of the battery, going through the thing, which might be a light bulb, and then coming out of the thing, which again might be a light bulb or a resistor, and into the negative side, which is the short leg of the battery. Okay. So that's always a necessity. There's your battery symbols I was telling you about, the long side being positive and the short side being negative. And they even take time to show you how to connect the batteries to a light bulb. That's in one of the earlier pages, so you can check that out. Current is going to be dq/dt. So you can imagine a gremlin sitting like right here in this little wire, and he's counting the number of electrons that go by in, by the way, the opposite direction of the actual current. And if he counts a certain number to go by in a second, he divides that number by the time and then multiplies it by the charge per electron. And that's actually dq/dt. So you need to be able to use that. I know we're 2 minutes long. Let me show you the rest of what I wanted to show you, because the rest of the stuff is just like stuff we've already done. V equals IR, that's Ohm's law, which we've done enough with in the lab. There's also the multipliers and the digits and the colors on the resistor. You don't have to memorize those, but we would give you a table if we wanted to do something like that. The resistance of a wire is directly proportional to the length of the wire. That's what the L is up there. Inversely proportional to the cross-sectional area of the wire, and proportional to this quantity called the resistivity, which is a property of the material. And that's, again, something we should be able to give you if you need it. And this is the temperature coefficient. So it turns out you can actually change the resistance, and it's the exact same equation as what we used when we were talking about heating up materials and how they expanded and contracted. Let me show you what that formula looks like real quick. There it is. This is resistivity, but you can also replace it with R and R0. So the resistance at temperature T is equal to the resistance at temperature T0 times parentheses 1 plus alpha parentheses T minus T0. That's exactly the same equation, except we had L and L0 before. So that's something totally done before. So it's not that big a deal. It talks about thermistors. I would say this is probably the most important chapter for you to read in terms of just knowing facts. Power, P equals IV, is one thing you're going to use. And the last thing that I really want to make sure you know how to do, and I'll work a problem for you next time, but it's to determine the actual drift velocity of the electric current. And the formula works out to be right here, E times N times V. So G is negative N times E times V, and J is basically the current divided by the area. And the negative is because electrons move the opposite direction as conventional current, and we're multiplying it by the electron charge. This example shows you how to calculate that in. Calculating that in is the only hard part of this problem. But those are the 3 or 4 equations: P equals IV in its equivalent forms, V equals IR, R equals rho L over A, R equals R0 parentheses 1 plus alpha parentheses T minus T0 close parentheses, close parentheses. And this guy is all you got to use for chapter 25. So I've told you about all of chapter 25, but I'll work examples next time, and you guys are free to go. Sorry for taking so long. Next time you will have a test in Mr. Mitchell's class. I'll talk to him. If him and I decide and we want you to do it during lecture time, we'll come up with something, but I don't think that's going to be the case, because I really need my lecture time, and I'm going to use that lab time to do the test. So feel free to text me. I have another class tomorrow at 10 a.m. and then a lab right after that at 12:45. Y'all can come by then. If you need me to set up a Zoom meeting for some extra help tomorrow, let me know. I can set it up, sometime during the day, sometimes during the night. I could also, get up with you Wednesday morning. My class does run from 10 a.m. Until 12:20, and then 12:45 my lab runs, but I'm available at 12:45. I think that's a little bit earlier than you start your lab. So those are awesome times you can get help. Just text me if you have specific problems you're working on and can't get it. Take a picture of it and send it to me in a text, and I'll do what I can to help you over the phone. Maybe even set up a Zoom meeting. But have a good one, everybody. Thank you for coming. Rohan, yes, you got something about John?
Yeah, Professor Young, I got a question about, like one of the equation you mentioned earlier today, it was the energy install, what's this? It's a 1/2 CV square. So
Oh, you talk about the energy is one
yeah, energy
zero
in
V
stall is
squared.
like U equals 1/2
Right.
CV squared. So I just had a I'm not sure, kind of confusing about it. So I understand the W on U is like the equation we had before was the W equals PV, right?
Right.
I mean QV, my bad.
Yeah, W is Q times the change in voltage times the charge is one way to do work. You
Right.
can also do FDL or something like that, right?
Yeah, so W equals QV, and so now we had that the EU is 1/2 QV. Basically, I just don't know where's the 1/2 from, because I understand the inner, the kind of energy install is just like amount of works, right? So we still talk about the works here. So
Right.
where's this 1/2 from?
Okay, when I did it, I said work is equal to QdV.
Uh-huh.
Q from the equation for the definition of a capacitor, Q is C times V, where C is the capacitance and V is the voltage. But C for a capacitor is just a constant, so I can pull that in front of the integral and I get the integral of V dV, and that's 1/2 V squared.
We actually, can you just write it down so I can kind of
Yes,
look at
I
it?
can do that.
Thank you.
Just turn this back on, turn this back on. And share with this. That's basically it.
Okay.
You can take
Okay.
integration from 0 volts to V volts.
So we use dV here. Is that because when you charge that thing, the first your V is probably it's kind of 0, and after you complete the charge, and that should be your power, and that should be your battery voltage, right?
Yeah, what your book did, maybe this will help you better. Your book said the integral of FDL, and they completely ignored the fact about the dot products and all that stuff. That's fine. We know that E is equal to F over Q. So F is E times Q. So this would be Q times E times DL.
Uh-huh.
When they do that, though, then you have to say, okay, well, Q is one of the things, but E could be V over L, and QE is just the force. So from there, you can actually integrate it, for instance, and plug in C times V for the actual charge. And then you can say V over L for that. So you get V squared. All sorts of stuff like that's a different one. What I was using was, remember our definition of the electron volt?
Mm-hmm.
That's equal to 1.602 times 10 to the negative 19th coulombs, which is Q, times 1.00 volts, which is delta V. So I'm using work, or D work is equal to Q
Oh, okay.
dV.
Oh, I see. I see this one.
That's that's what
Yeah.
I used.
Yeah, I was wondering. So, and also one that, okay, that's why the unit for that is also joule. Okay.
Exactly. And remember, work is sort of what we use to calculate potential energy, because the work you put into the system gives it a certain amount of energy that has the potential to do work again. So that's, that's how
Right.
you drive kinetic energy and all that stuff.
Okay. Oh, I see. All right. Thank you so much, Professor Younger. And
No problem.
I just want to say that so I had a lot going on for the past week, and I've been trying to catch up the homework, all that kind of stuff. and just because there's a lot of information I need to actually spend time on study,
Right.
and I do feel I don't really feel comfortable to take this this exam,
Right.
especially with my my first and the second in-person test. I kind of feel good, happy with my grade, current grade. So I just wish I can spend like more time to actually catch up all the homework and prepare for the final. If you allow me, if I can skip this in-person test, I mean the Wednesday test, because
Yeah.
I think
I don't mind you. I don't mind you skipping it. And like I said, it probably would be more important for you to get a lot more homework done just because your test grades have been good.
Yeah, I mean, I still work. I will do work on the practice test. Actually, I did a practice test last night. Uh, wasn't that bad, but it's just a lot of information that I need to like kind of
refresh
try to
yourself
I need
on.
to put them together. So
Right.
right now, like there's a lot of formula in my head, but I need to kind of spend some time to add them like together to one page. So
Right.
yeah, I try to just spend more time on to
No
prepare
problem.
the final. Yeah.
Yeah, go ahead. It's not a big deal. Like I said, I did tell you guys that I was going to give you the high two, and you certainly did well enough on the second one and the first one for that matter. But the second one's an important one. So yeah, it's fine if you miss. Even if you want, I can still everybody's taken it, I can give you a copy so you can use it to study or whatever when you're
Oh,
doing.
sure. That'll be great.
Okay,
Thank you so much, Professor Younger.
you're welcome. Have a good one, Bohan.
Oh, thank you. You too.
Bye bye. John,
Bye-bye.
are you still here?
Yes, I'm still here. Yeah, sorry I came in late. I was stuck in traffic and my commute from lab is about like an hour and 10 minutes long.
Oh, great.
Uh,
Yeah.
yeah, so with traffic it's a little longer. I wasn't able to make it within the first 30 minutes of class. I was
Mhm.
wondering, was that recorded? And is that something
Yes, it was
Okay.
recorded, and
Okay.
you can look at the comments, the chat. I think you can still look at it, and you'll see two messages that I sent out about what chapters are extra credit on homework, and
Okay.
and then there's another one about when the final is, and then there's another one that's the announcement that's in Canvas, so you can see that in the chat as well. But yeah, I did record all that, and that should be up sometime tonight.
Okay. Yeah. Unfortunately, I can't see the chats that were posted before I logged on, but yeah,
Hold
I'll
on,
take a look.
I'm gonna put them up there again real quick. Let's see if I can do that.
Okay.
Okay, so this is the first two that I sent. Oh, I had it connected to the wrong person. Hold on. '31st of July. So that's when your final is. And notice the only chapters that actually count are there it is. Yeah, it appears. Yeah. Yeah, so I did that. And then this is what Nora posted, which is the actual announcement that I put in Canvas. So let me share this with you.
Yeah. And I did see the announcement.
You did see that. Okay, cool. Well, that's all the chat that it was. So I was looking at the calendar wrong, and for some reason I thought the August 1st was Monday and August 2nd was Tuesday, but it turns out August 31st is Monday and Wednesday's August 2nd. So that allowed me to push our final back to the 31st, which is what day it'll be.
Okay. Got it. And then when it says so the only chapters that are not extra credit, and then it lists the chapters, what is that exactly?
Okay, so basically the chat. Ideally, I'd like to get through 31 chapters 17 through 21 in this whole course. I don't think I'm going to get through, but maybe 28. So if I make it to 28, then 1 through 28 will be required, but everything before or outside of that, like some of them I put up there, like chapter 30, 38 and 39 and 40, some of those homeworks are up there and they're not marked EC, but they are extra credit. So I'm just saying anything other than those numbers is definitely extra credit. And if I don't get to 28, then 28 will be extra credit. If I don't get to 27, then 27 will be extra credit.
Got it, got it. Okay, sorry, give me 1 second. I'm just reading the messages real quick. Okay, got it, got it. All right, I think that answers most of my problems. Yeah, I'm a little behind on material and whatnot. Um, like worst comes to worst, I figured I might just have to retake it. Which obviously I don't want to do, but at the same time, I want to make sure that, I'm understanding the information and that I have that information, in my brain, obviously.
Yeah,
You
past
know,
class that you didn't understand can often be, doing you continuous harm. So yeah, I get you. I
yeah.
did tell them that the last test and this test, you're only going to get one of those scores, and it's the higher of the two. So
The midterm, correct?
yeah, so the midterm and this test, whichever one of those is the highest, I'm going to give you that score and erase the other score. Specifically because I had some issues with some students didn't know the charge of an electron. Some students didn't turn in the work like they were supposed to because they went to the testing center and then the testing center didn't take it up. So the easiest way for me to fix that is just say, hey, I'm going to give you the higher of these two and it'll count twice.
Okay, got it.
Okay.
Okay, sounds good. All right, thank you so much.
No problem. Have a good one.
Bye bye.